Okay, so I'm going to do every exam question that has been asked. It's going to be on angles, but in particular, it's actually going to be about circle theorems. Now, circle theorems, there are so many questions. I'm probably going to have to split this into two parts as well. Now, unfortunately, this first question is a pretty tricky one, but let's see if we can do this one. It says ABCD endpoints on the circumference of a circle. Great, we can see that. And FDE is a tangent to the circle. Show that y minus x equals 90, and you must give a reason for each stage of your working. So I think one of the most obvious things that I can do here is I can say that this angle, ODE, is 90 degrees. So I'm going to write down that angle ODE is 90 degrees. And the reason for that is that it's a radius and a tangent. A radius and tangent, they meet at 90 degrees. And I think that's the minimum of what we're going to need to say here. If you look on these rules, it's tangent and radius. As long as you've got those words, it's enough for this kind of thing. Now I'm going to see if I can think about what some of these other angles might be in this one. Well, I can tell that because of the alternate segment theorem, that this angle here, this blue one that I've got, the alternate segment theorem, which is BDE, is going to be the same as y. Now the reason that is because on either side of this line, this is one segment of the circle, and this is another segment of the circle. This line, this angle here with the tangent is the same as this one that's in the alternate or the different segment to it. So I'm now going to say that angle BDE is, I don't know why I put a little degree sign next to the ODE, angle BDE is equal to y degrees, and the reason for that is the alternate segment theorem. So we can just say alternate segment, and we don't even need to say alternate segment theorem. You can see here it just wants us to say alternate segment as the bare minimum. Okay, now we can see that the angle x, which is BDO, so x is equal to the angle y minus 90. And that's because it is BDO minus ODE. So if I want to add in a little bit of extra detail there, I can say that x is equal to angle BDE minus ODE. BDE minus ODE, which is y minus 90. Now all I need to do is a little bit of rearranging here. So I'm going to add the 90 to this side. So I have 90 plus x equals y, and then I'm going to subtract the x so that I get 90 equals y minus x. And we've given a reason for each stage of the working there. Dylan was asked to give some possible values for x and y, and he said, well, y could be 200 and x could be 110, because 200 minus 110 is 90. Well, he's correct in the sense that 200 minus 110 is 90, but we need to look at the diagram. Is it possible that y could be 200 degrees? And the answer is no. Y cannot. So I'm going to say no, and the reason is y cannot be 200, as angles in a triangle only add to 180. Angles in a triangle add to 180, so there's no way that it could be bigger than that, okay? So a bit difficult to see this because it was a show that question, but the explanation, no, y must be less than 180 because it's an angle in a triangle. So we've got that part answered there as well. So we have here A and B are points on a circle centre O. BC is a tangent to the circle. So as soon as I see tangent, I know I'm going to want to try and do that tangent and radius rule. AOC is a straight line, and angle ABO equals x. So ABO, I'm going to draw this line in here. I don't know why they didn't give it to us. That angle is x. Find the size of angle ACB in terms of x, give your answer in its simplest form, and give reasons. So the one that we're eventually aiming for is ACB, which is this one. This is the goal that we've got over here. So there's a couple of different things that we should notice. First of all, I think we can find out what that angle there is, which is angle OBC equals 90 degrees, and that is because it is a tangent and a radius. It's a tangent and radius. Now I'm going to think what this angle at the top is. So this is angle OAB. Well, angle OAB is also going to be equal to x. The reason that it's equal to x is because this line and this line are radius. So they must be the same as each other, which means this must be an isosceles triangle. So now I'm going to try and find out this one that we've got at the top, which is angle AOB. Now angle AOB would be 180 minus x, which is 180 minus 2x. So that angle is 180 minus 2x. Now I'm going to find out what the one next door to it is. The one next door to it is angle BOC. angle BOC. Now, you could do 180 minus 180 minus 2x, or you could just think to yourself, if this is 180 minus 2x, this one over here must be equal to 2x. So, I didn't say that the reason for this was isosceles triangle, and this was angles in a triangle. And the reason that that one must be equal to 2x is because it is a straight line. So this one must be equal to 2x. So my last thing, my goal that I'm going to say here, angle OBC is 180 minus the right angle, which is 90, minus the 2x. And 180 minus 90 is 90. So it is 90 minus 2x. And the reason for that is angles in a triangle. Angles in a triangle. So we've definitely given loads of reasons there, and we've come up with 90 minus 2x. 90 minus 2x, just note the ones that are underlined are the ones that have to be written down to be able to get them, okay? So I guess I should have said angles on a straight line, so I'm going to say that here, angles on a straight line. Angles on a straight line. Okay, let's have a go at the next question. Finally, there's ones with numbers rather than just algebra. We need to show all our working, but we don't need to give all of our reasons. Now, working can be on the diagram, so that is perfectly fine for us to do. I am going to be rotating my iPad so that I can draw these angles where I want them to be, but you should be rotating your paper when you try these kinds of questions. So I'm going to begin by doing the alternate segment theorem. You can see that this angle here is 56, which means the one on the alternate segment of that line, meaning this is one segment and this is another segment, that is going to be this is a 56 degrees that we've got here. Now, if I was going to give a reason, I could say that the angle at the centre is double the angle at the circumference, and double 56 is 112. Now that I've got that, I haven't even read what the question says. You must, work out the size of angle CAO. So let's put where our goal is, CAO. This is the one in red that I'm trying to work out. And there's other ways you could do this. The way my brain sees this is think, let's work out what that one there is going to be. Well, it's going to be 360 minus 112. So I'll borrow the 1 from the 5. 10 take away 2 is 8. 5 take away 4 is 1. And 3 take away 2 is 248. So the angle that I'm going to try and work out, which is this one here, I'm going to do 360 minus the 35, the 56, and the 248, because it is a 1, 2, 3, 4-sided shape. So I'm going to do 248, 56, and 35. I'm going to add those together and then take it away from 360. So 8 plus 6 is 14, plus the 5 is 19. 4 plus 5 is 9, plus the 3 is 12, plus that is 13. And then the 2 plus the 1 is 339. So I'll do 360 minus 339. I could do this borrowing method. It's going to be pretty obvious what the answer is. 35 take away 33 is 32. So it is 21 degrees. So they would even accept the answer if it was drawn on the diagram. But I'm going to write it down at the bottom that angle CAO is equal to 21 degrees. Let's double check we've got this right. So we've got 21 degrees and absolutely no reasons were needed to give for this. It says reasons do not need to be given, so I wouldn't give them. Okay, we have the point A, B, C and D lying on a circle. CDE is a straight line. It is not a tangent, so we will not be reusing that rule. They've told us that BA equals BD, so this is an isosceles triangle. And they've said that CB equals CD, so this is an isosceles triangle. And the goal that we have here is to work out ADE. This is the goal that we're going to try and do, and we need to give a reason for each stage in this working. So I'm going to write down these two angles. I know that this triangle that we have here is isosceles, so I'm going to take away 40 from 180 and then half it. So if I do 180, if I take away 40 and then half it, I get 140 divided by 2, which is 70. So these are 70. So I'm going to write down that angle BAD is equal to angle BDA, which is 70 degrees, and my reason is isosceles triangle. Now I'm going to think about what other angles I could find out. I don't think I can do the alternate segment theorem because I don't have a tangent. I can't do the tangent and radius because I don't have the tangent. But I do have this shape. I do have ABCD. ABCD is a cyclic quadrilateral, which means the opposite angles in a cyclic quadrilateral are equal to each other. So I can work out what angle BCD is. they're not equal to each other, excuse me. The opposite angles in a cyclic quadrilateral add to 180. So this one and this one needs to add to 180. So I'll do 180 take away 70, which is 110. And this is because they are opposite angles in a cyclic quadrilateral, and they are looking for all of those words that we have there. Now I know that this is 110, I can find out what these angles are for the same reason. I can do 180, take away 110 and divide it by 2 because it's an isosceles triangle. That is 35 degrees. So there's a 35 there and a 35 there. So I'm going to say that angle CDB is equal to 35 degrees. I could also say that it's the same as angle CBD as well, but that's equal to 35 degrees because it is an isosceles triangle. And now we can find out the one that we want, angle ADE. It would be 180, take away the 70, take away the 35. So that's 180, take away 105. So it is 75 degrees. And the reason is because of angles in a triangle. So let's double check we've got this one right. 75 degrees with reasons. Great. And as I said before, if it's underlined, the word has to be there, okay? Okay, let's see if I can just do one more before I might pause this video because these are quite long to film. It says that A and B are points on a circle with centre O. CAD is the tangent. So as soon as we see tangent, I want to use that rule. And BOD is a straight line. Great, I can see that. And angle ODA is 32. Work out the size of angle CAB. You must show all your working. However, you don't need to give reasons. So the goal that we're going for, CAB, is this one over here. Well, I know immediately that that one is going to be 90 degrees. Okay, that one has to be 90 degrees that we have. And I think we can also do the alternate segment theorem. So this creates two segments, okay? It creates this side of the circle and it creates this side of the circle, which means that this angle, actually I don't think we can do the alternate segment theorem here. Let me just quickly get rid of that line because I don't think we can do. What we can do in this one is... silly me, of course, we can find out this angle at the top here. So it's a calculator one, but I'm just going to do the 180 minus the 90 minus the 32 to find that one that's at the top. Very silly of me thinking I could do the alternate segment theorem. I definitely can't do that here because we don't have it going to the other side of the circle. So we get 58. So this one here is 58, which means the one next to it is 180 minus 58. So I'll do 180 minus the answer, so that is 122. Now this shape that we have here is an isosceles triangle, so I can do, that was 58, I can do 180 minus 122, and I can half that. So I'll do 180 minus 122, and I'll divide it by 2, and I get 29. So they will be looking at your diagrams for these, so that's a 29, and that's a 29. Now, because that's a 90, I can just do 180 minus 29 minus 90, and it will give me our angle CAB, which is the one that's in red. So CAB is 180 minus 29 minus 90, which is 61. So we have 61 degrees for our red angle. I'm going to put it on this diagram, and we have done this showing all of our working. Let's double check that we've got this one correct. Yep, it is 61 degrees. I'm going to take a brief pause, but we'll continue the video for you, so it's all uploaded as one thing. Okay, next question, we have got this one here. So it says that BD, E and F lie on a circle, ABC is a tangent to the circle at B, find the size of angle ABD. You must give a reason for each stage of your working that we've got here. Well, we've got this special shape, which is a cyclic quadrilateral. So I think immediately we can work out the size of this angle. Cyclic quadrilaterals, opposite angles add to 180, which means that that angle is 80 degrees. So I'm just going to write down that angle DBF is equal to 80 degrees, and that's because they are opposite angles in a cyclic quadrilateral. Opposite angles in a cyclic quadrilateral. And now I'm going to think about what else I could find out. Well, I'm trying to find out what the size of angle ABD is, so that's my goal. And if you think about what's going on here, we've actually got two segments of a circle, and so I know that the angle over here is going to be the same as this one. And I can actually just find out what that angle is because this angle is part of a triangle, which means they have to add up to 180. So it's from a calculator paper, so I can just say that angle BFD is going to be 180 minus 80 minus 40, which is 60 degrees, and that's our angles in a triangle. And so the last one that we're going to have is just to say what angle ABD is. Angle ABD is equal to 60 degrees, and that's because of the alternate segment theorem. I don't even think we need the word theorem, but it should be there really. Let's have a look at what the mark scheme says. So we've got 60 degrees for our final answer. I do it in red because that's the one that we were aiming for. So we've got 60 degrees, and they're looking for the opposite angles of a cyclic quadrilateral and then the alternate segment theorem. So remember, the underlined words are the ones that need to be done, and it does say they need to have the reasons linked to the method. Okay, let's have a look at this one that we've got here. It says that ABCD are 4 points in a circle. SBT is a tangent to the circle, and angle ABD is 20 that I can see here. It then says that the size of angle BAD, this one, as a ratio of the size to angle BCD, which is this one, is 3 to 1. So the angle at the top is triple the size of the one down here. So if I call that one x, that one would be 3x. And I know something about these two things. I know that the opposite angles in a cyclic quadrilateral add up to 180. So I'm going to write down here that 3x plus x equals 180. And I'm going to give a reason for that. I'm still going to write down that this is opposite angles in a cyclic quadrilateral. So I'm going to solve this. 4x is equal to 180, and on a calculator, 80 divided by 4 is 45 degrees. So I'm now actually going to say that angle BAD is 45 times 3, and 45 times 3 is 135, and we know that angle BCD is just equal to 45 degrees. So I can replace that on the diagram. I'm going to say this one is 45 and this one is 135. Now the one that we're aiming for was SBA, which is this one. And as soon as I have a tangent and a line, I think, okay, I've got this small segment of the circle and this big one. So actually it's going to be equal to that one that we have over here. I'm going to begin then, well, I'm not going to begin, I'm going to continue by finding this angle. The next one I'm going to find is angle BDA, and that's going to be equal to 180 minus 135 minus 20. So that's 180 minus 155. That is 25 degrees. So BDA is 25 degrees, and that's because of angles in a triangle. Angles in a triangle. And so we're going to do our last part now, which is to say that angle SBA is equal to 25 degrees, and that's because of the alternate segment theorem. Okay, so there's our final answer of 25 degrees. Let's double check we've got it right. Yep, we do have the 25 degrees that we've got right here. And so we got all the extra bits for the reasons. There are 2 marks reserved for the reasons. Now we're moving on to some proof kind of questions, which do tend to be more challenging. It says ABCD are 4 points on the circumference of a circle. AEC and BED are straight lines. Great, we can see all of this. Prove that triangle ABE and triangle DCE are similar. You must give reasons for each stage of your working. So the 2 triangles we're looking at is this ABE triangle that we have here. And then the second triangle that we want to be similar is DC and E. Now, if triangles are similar, it doesn't mean they're exactly the same, but it does mean that they have the same angles. So first of all, I'm just going to write down a note. Similar means that it has the same angles. So I need to do that for all 3 of them. I'm going to start off with the easiest ones that we have over here. I'm going to say that angle AEB is equal to angle DEC, or CED, whichever way we want to do that. And the reason, because it's a proof question, we want to give these reasons. It's because vertically opposite angles are equal. Vertically opposite angles are equal. I don't think we need the are equal bit, but we're going to go for it. Now what I want to try and do is I want to prove that this angle at the top is going to be the same as this one. And the reason that they're the same is because of the angles in the same segment. If you draw that line, you've got kind of this triangle and this triangle. So it's the angles in a same segment. So I'm now going to write down that angle ABD is equal to angle ACD. And I'm also going to do the same thing for the other side. If this was my segment line, I could say that this angle, which I'm going to do with 3 lines, is the same as this one that we've got here. So I'm going to write both of these things down, and then I'm going to give it the reason, which is the angles in the same segment are equal. So this one is BAE, and then we have BDC. BDC. And the reasons for both of these is it's angles in the same segment. Angles in the same segment. And then we're just going to do a concluding statement to show that they are similar. Because they have the same angles, they have all the same angles, or they have all the same angles, the triangles are similar. Okay, so mark scheme's not super clear for this, but the reasons we are looking for are the angles in the same segment and the vertically opposite or opposite angles that we've got as well. Okay, now we have another kind of proof question. This one's really weird because we've got these points on the circumference of a circle, A, B and C, and AOB is the diameter. And we want to prove that angle ACB is 90 degrees, but we must not use any circle theorems to do this. So we kind of have to forget about circle theorems and try and prove that it is going to be 90 degrees. Now there are lots of different ways of doing this, but I think this is the way my brain is going to see this. Now, I put an extra line on here because then what I've done is I've created something where all of these are the same length because they're going from the center to the outside, so they're all the radius, which means I have got two isosceles triangles. Now, if I call this angle here x, and that would mean that this angle here is also going to be equal to x. So I'm just going to write that down. I'm going to say if angle OCA equals x, then I'm going to write down that angle OAC equals x, and the reason is because of the base angles in an isosceles triangle. Base angles in an isosceles are equal. Base angles in an isosceles are equal. Now I'm going to do the same kind of thing over here. I'm going to now call this one y, which means this one is y. So if angle OCB is equal to y, I'm going to literally write the same process, then angle OBC equals y, and it's the same reason. Base angles in an isosceles are equal. And now I'm going to finish up by having a look at this whole shape that we've got. I'm going to look at triangle ABC. So if I look at triangle ABC, I'm going to look at this angle, and this angle, and see what we get. So I get that x plus, this angle here is x plus y because there's those two together. So x plus y, and then my last angle is y, and that is equal to 180 degrees because it's angles in a triangle. So I get 2x plus 2y is equal to 180. And then if I divide everything by 2, I get x plus y is equal to 90 degrees. Hence, angle ACB is equal to 90 degrees because angle ACB is the x plus y added together. Now, there are a few different ways of doing this. This is just the way that I see this, and I think it's probably going to match up with the mark scheme. So we've got an extra line drawn in for OC, and we've got the sum of an angles in a triangle. And, oh, they did actually want the extra reason. The base angles in an isosceles, angles in a triangle add up to 180. So I think I might need to do a little reason here and say angles in a triangle add to 180, just to make it really clear that I've given every reason, because I guess it is a proof question, so we do want that. Okay, this one that we have, this is really quite an odd question because we've got these two triangles overlapping. It basically says A, B, R and P are 4 points on a circle with this centre, A, O, R and C are 4 points on a different circle that we have, and we don't have its centre. The two circles intersect at the points A and R. This is a straight line, this is a straight line, and this is a straight line, and we want to prove that angle CAB is the same as angle ABC. So CAB is at the top. And what I'm going to do is try and prove that it's the same as angle ABC. So kind of that's the goal of what I've got over here. Now, if I were to call this one X, I think that might be like a kind of a good starting point for what we've got there. And I'm actually going to draw in some other things that I think could be useful. Now, from O to R is going to be a radius. And as soon as that's a radius, I know that line is the same as that line, which is the same as that line. And if you look at this circle that we've got over here, I think I should be able to tell what this angle is because looking at this circle, I have got a cyclic quadrilateral by having added that thing in. So I'm going to say let's just do this in blue. So I'm going to say let angle, what is it, OAC equal x. No, CAB, that's the one they wanted us to say, CAB. Let angle CAB equal x, CAB equal x. Then I would say that ORC, angle ORC, would be equal to, because it's angles in a cyclic quadrilateral, it'd be 180 degrees minus x. And the reason is because opposite angles in a cyclic quadrilateral. Opposite angles in a cyclic quadrilateral. Now if I go to this part of the diagram, I can find out what ORB is. So angle ORB must be equal to x, and that's because of angles on a straight line. Angles on a line. They add up to 180, so this one here has got to be x. Which then tells me, if I continue with my proof up here, that angle OBR, should I call it OBR? I'm actually going to call it ABC because I think we've proven it. ABC, no, we'll say OBR, which is equal to angle ABC, is equal to x. And the reason that it's equal to x is because it is an isosceles triangle. So I'm going to write down the reason that the base angles in an isosceles triangle are equal. Base angles in an isosceles are equal. Hence, angle ABC is equal to angle CAB, because they're both equal to x. So it doesn't look like there's much working. The diagram's quite useful to help you with this, and that extra line really helped by adding on that radius. So there's the proof. They talk about the opposite sides of the cyclic quadrilateral, angles on a line, etc., etc. Now this one I've actually covered in the congruency video. So in terms of saving a bit of time here, this is one where you're trying to prove that there are matching sides and matching angles. If you want to read through the working out, you've got it here. If you want to see the video of me going through this one, it's the third question in the congruency video. It should be very easy to find, and you can just skip through to that one so that I'm not repeating and making this video even longer. I just put it in 2 locations because I thought it was a question that should be in both places. Okay, and then we've got this one here that kind of pulls in some other things. You'll notice up here I've added some extra stuff. It's including trigonometry and it's including arc length. So it says ABC are points in a circle of radius 5 centimeters and center O. Great, I can see that. DA and DC are tangents to the circle. So as soon as I see that there are tangents to the circle, I immediately know that a tangent meets a radius at 90 degrees. So I want to add that onto the diagram. And it says that DO is 9 centimeters, so I also want to add that. Work out the length of arc ABC. So it actually wants us to work out, if I highlight this in a blue colour, it wants us to work out this length that we have here. It wants us to work out this big one. So I think in order to work out that length, we need to find out what the angle over there is, which means I need to find out what these angles are, which I can do straight away. So I'm going to draw a picture of one of these triangles. I'm going to draw this yellow triangle separately, and that might help us figure out what's going on here. So when I draw that yellow triangle, which I have here, we have the O, the C, and the D part. I'm going to just highlight this in yellow to make it really clear what I've drawn. Now that OD length is 9 centimeters and the OC length is 5 centimeters, and we want to find out what this angle here at the top is, okay? If I call that angle X, we're going to set up using trigonometry. Now I've got the adjacent and I've got the hypotenuse. So I'm going to say that the cos of X is the adjacent over the hypotenuse. So I'm going to find out what X is equal to by doing the inverse cos of 5 over 9. And I'm going to put that straight onto my calculator here. So I'm going to do the inverse cos of 5 over 9. And it gives me 56.251 or 56.25 degrees. 56.25 degrees. I'll tell you what, I'm going to do 251 just in case we need a little bit more accuracy. So if these ones here, this is 56.251, this one is going to be 56.251 as well. So if I want to find out what this angle here is y, I can say that y is equal to 360 minus 2 times 56.251. I'm going to just do that on my calculator. It's already stored as the answer on my calculator. So I can do 360 minus 2 of the answer, which is 247.4979, blah, blah, blah. So all I need to do is to find the arc length of this section. So the arc ABC, well, the whole circle is going to be the circumference of the whole circle. That would be pi multiplied by the diameter, which is pi multiplied by 10 in this case. But I don't have the whole circle. I have got some fraction of 360 degrees. And out of those 360 degrees, I've got this value, which is y. So I have the 247.49 blah, blah, blah. And that's going to get multiplied by pi over 10. So because I've already got it on my calculator, I can literally just type in answer divided by 360, multiply it by pi, and then multiply it by 10 for the diameter. And to three significant figures, it's going to be 21.6. So it is 21.6 centimetres for the arc length that we've got there. Let's double check we've got this one right. Yep, there's the 21.6 that we have. Now that is everything that is on angles, and we've covered tons of stuff in these few videos, from parallel lines and triangles and polygons all the way through to these kinds of circle theorems. If you've hung around for all of this, well done, because this is a challenging topic. It would be very helpful for me if you could like this video, even subscribe to the channel, share it with any friends who are doing their GCSEs, and just wishing you the best of luck for your studies.